So, we have seen the basic definitions and some basic properties of groups. We have seen what is meant by subgroup. Today, we are going to start looking at another property of a group called the class of a group. Okay. In order to do that, first we will define something called a similarity transformation. So we will define something called a similarity transformation. Okay. In order to define this, so let A be a member of G. Okay, this is the group. Okay, so A is a member of the group. Okay, and X is also a member of the group. So X is also a member of the group. Okay, then B is equal to X inverse A X. Okay. This operation where you multiply A by X on the right and X inverse on the left is called a similarity transformation. And B and A, these two elements B and A are said to be conjugate to each other. So, you say B is conjugate to A. Or you can also say, you can easily show that if B is conjugate to A, then A is also conjugate to B. Okay, so you can show that by this. Now, if I pre-multiply by X, so clearly B X inverse. Okay, so I multiply on this side by X. So here I multiply by X, X times X inverse is 1. Then I multiply on the right by X inverse. So here if I multiply on the right by X inverse, then I just get A. So okay, so therefore A is conjugate to B. So if B is conjugate to A, then A is conjugate to B. So implies A is conjugate to B. Or you can say that A and B are conjugate. A and B are conjugate elements. Now, suppose we consider an element A. So, A contained in G, and let's say the for all X contained in G, we calculate X inverse A X. Okay. So, for all X, this is X contained in G. So, for all the elements of G, we calculate X inverse A X. Okay. So, A is the same. So, A is one element of G. Okay. So, then this will lead this, in some cases it will just yield A, in some cases it will be in some cases it will give you something else. But this set of elements, okay, for different choices of X, this set of elements is called a conjugacy class. Okay. So, the conjugacy class consists of all elements that are conjugate to an element. The other thing I should mention is that if B is conjugate to A, so I'll just, B is conjugate to A, we write it as B is conjugate to A. Okay, this is the notation. So, if B is conjugate to A and C is conjugate to A, clearly B is conjugate to C. Okay. So, let us show this. Okay. So, if B is conjugate to A, then it's B is equal to X 1 A or X 1 inverse A X 1, and C is conjugate to A implies C is equal to X 2 inverse A X 2. Okay. And I can easily do the following. I can put an X 2 inverse X 2 here. So I can just say that B is x1 inverse, and then I'll just multiply by 1. So, I multiply by 1 in the form of x2 inverse x2 a. Okay. Then again I multiply by 1 and I multiply in the form of x2 inverse x2 x1. Okay. So, I just multiplied by 1 here, multiplied by identity here and identity here, okay, because x2 inverse x2 is just identity. So, and I can always multiply by identity, it does not change anything. Here also I multiplied by the identity. Okay. So, this is equal to x1 inverse x2 inverse, that is same as x2 x1 the whole inverse, okay, times x2 a x2 inverse. I should have done it the other way. I should have done this the other way. I will just do this as I will put x2 x2 inverse here and x2 inverse x2 here, or x2 x2 inverse. Okay. So, I will just do it in this order. Okay. So, then this will be x2 inverse x1 the whole thing inverse. Okay. This is x2 inverse x1 the whole thing inverse, and then this whole thing is just x2 inverse a x2, that is c, and here you have x2 inverse x1, x2 inverse x1. So, what I have is if I call x3 x2 inverse x1, then B is equal to x3 inverse C x3 implies B is conjugate to C. Okay. So, what we showed that if we had B is conjugate to A and C is conjugate to A, then clearly B is conjugate to C. So, then the set of all these elements that are conjugate to each other, they form something called a conjugacy class. Okay. So, all elements are conjugate to each other. Okay. So, this idea of conjugacy class will be very useful when we are describing the groups of interest to molecular symmetry. So, let us take an example, okay, to make the idea of both classes and subgroups clear. Okay. So, the example I will take is the dihedral group of order 6. Okay. So, the dihedral group of order 6. So, what does this corresponds to? This corresponds to the set of symmetry of plane symmetry elements of a three-sided of a triangle. Actually, a three-sided polygon is a triangle. Okay, triangle. Okay, of a regular triangle. So basically, suppose you had a triangle, and let me call this A, B, C. Okay. Now I have various symmetry operations. So, for example, if I rotate by 120 degrees, 20 degrees, okay, to this way in this sense, then I will get C, A, B, and then I can rotate by 240 degrees, then I will get A, B, C. Then I can consider a reflection about a plane passing through A, okay, and the midpoint of the other two. So, that will give me A, C, B, and I can consider two more reflections, sigma C, B, C, A, C, B, A. Okay. So, there are 5 operations, and then the 6th operation is the identity operation, where you do not do anything. Okay. So, the 6th operation is the identity. So, there is also the identity operation. Okay. Now, these 6 operations, okay, it is these 6 operations which will be taken to form a group. So, the 6 symmetry operations form a group. Okay. And we can write the multiplication table of this group. So, we have E R 120 R 240 sigma A sigma B sigma C, okay, and I have E okay, and I choose to define my sigma A as rotation with respect to this point, with respect to the top point. Okay. Sigma B is rotation with respect to this point, and sigma C is rotation with respect to this point. Okay. So, it is always this point. So, even if I do sigma B twice, I will always reflect, sorry, these are reflections. So, I will always reflect about a plane, about this plane. Okay. So, clearly you can look at this and you can say that you can write the first row, okay. Similarly, you can write the first column, okay. So, this part is easy. Then you ask, what is the product of these two operations? So, that means you operate first by R120 and then again by R120, and it is very obvious to see that if I rotate once by 120 degrees and I rotate again by 120 degrees, that corresponds to rotation by 240 degrees. Okay. And rotation by 120 followed by 240 is nothing but the identity, and you can fill in this part quite easily. Okay. So, this part is fairly easy. Now, suppose I do sigma sigma A and I again do sigma A. So, I reflect about this plane and then again reflect about this plane, that is nothing but the identity. So, this is identity, and similarly this is identity and this is identity. So, this much you can write fairly easily. Next, you have to consider what happens when you do sigma A first and then R120. Okay. So, what I am going to write here is R120 sigma A, that means I operate first by sigma A and then by R120. So, if I operate by sigma A, then basically I get A C B, and then I follow it by R120 degrees, then I will get B A C. Okay. So, B A C, okay. And notice that C is where it is, B and A are switched. So, that corresponds to sigma C. So, this is sigma C. Similarly, you can show that this is sigma B. Okay. And this will be okay. Now, if I do R120 and I follow it by sigma or I do sigma B followed by R120, you can easily show that this will be sigma A. So, I do sigma B and then rotate by 120 degrees, and A is where it is, B and C are swapped. So, it is sigma A. You can show this. Okay. This is not hard to show. Now, what if I do it in the reverse order? So, first I rotate by 120 degrees and then I do sigma A. So, first if I rotate by 120 degrees, then I get A, B, C. Now, if I do sigma A, if I flip it about this, then I have C, A, B. Okay. So, now B is where it started. Okay. So, it corresponds to sigma B. Okay. And this will correspond to sigma C. This will correspond to sigma So, if you do R120 and then followed by sigma B, So, R 120 and then you do by sigma b about this, okay. Then you have A here, B here, C here. So, that is sigma c. This will be sigma A, this should be sigma b. Okay. So, that should be. And now what about sigma A, sigma b? So, first you do sigma b and then you do sigma A. So, first you do sigma b, that will correspond to this. So, you will get this. Now, if I reflect about this, then I have C A B. Okay, so, I have C A B, and you can clearly see that this corresponds to rotation by 120 degrees. Okay. So, this is R 120, this will be R 240, this will be R 120. Okay. So, you can verify this multiplication table, okay, of this group. This is dihedral group of order 6. Okay. Now, next we want to identify the subgroups and the classes of this group. Okay. So, we want to identify the subgroups and the classes. So, let us start with the subgroups. Okay. Now, a subgroup is a part of a group that itself looks like a group. Okay. Now, if you just look at the multiplication table and you look at these elements E R 120 R 240. Okay. So, these, so if you just look at E R 120 R 240, okay, 40, okay. So, clearly this is a group because it has because inverse of R 120 is R 240, because R 120 nothing but identity. Okay. So, it has 3 elements, it is a group of order 3. Okay. So, this is a group of order 3. Okay. Are there other groups in here? Okay. So, well, you can always construct a group like E sigma A. Because sigma A, inverse of sigma A is sigma A itself, inverse of sigma A is just sigma A, because sigma A square is identity. So, this is a group. Similarly, E sigma B. So, these are all the subgroups. Okay. So, all these will be the subgroups of this group. Okay. Are there any other subgroups of this group? And I do not see any other subgroup. Okay. So, I do not see any other subgroup, because if you involve 2 of the sigmas, if you involve any 2 sigmas, then you get rotation. So, you have to involve rotations. Okay. And the only other subgroup is the entire group. Okay. So, G. Okay. And in addition, so there is always this trivial subgroup which is G itself and identity. So, these two are the trivial subgroups. So, for every group the identity will be a subgroup and the entire group G itself will also be a subgroup. Okay. So, these are the subgroups. In addition, there is 1, 2, 3, 4, we have identified 4 subgroups. The orders of the subgroup, this is a subgroup of order 3 and these 3 are subgroups of order 2, and notice that the order of the subgroup divides 6. So, 6 is the order of the group, order of the subgroup divides the order of the group. Okay. So, the subgroups, this is how much we can say about the subgroups. Now, what about the classes? Okay. So, what about the classes? So, statement I will make is that E is in a class by itself. Because X E X, X inverse X E is equal to E for all x contained in G. So, you take E for any group, this is true for any group, E is always a class in itself, because x inverse E is just x inverse. So, x inverse E x is always equal to E. So, the only element that is conjugate to E is E itself. Okay. So, R 120, R 240 form a class. Okay. And you can verify this because suppose I take R 120, okay, and I multiply it on the right by sigma. So, for example, consider, so suppose I take E R 120 or E inverse R 120 E. E inverse is just E identity, the inverse of the identity is the identity, R 120 into E. So, this is R 120. Then you consider R 120 inverse R 120 R 120. Then you consider R 240 inverse R 120 R 240. Then you consider sigma A inverse R 120 sigma A, and then similarly you will do for sigma B and sigma C. So, this will give you the set of all elements that are conjugate to R 120. Now, R 120 inverse R 120 is E. So, E into R 120 is just R 120. R 240 inverse R 120 R 240. So, R 120 into R 240 is identity. Identity into R 240 inverse is just R 240 inverse, which is R 120. Now, what about sigma A inverse R 120 sigma A? So, first you operate by sigma A and then R 120. So, that gives you sigma C. Okay. So, you have sigma C multiplying sigma A inverse. Sigma A inverse is just sigma A. So, sigma C into sigma A is R 240. Okay. Similarly, if you do sigma B and sigma C, you will get R. So, if I do sigma B, I'll just write it here. Sigma B. So, if I do sigma B inverse, that is just sigma B R 120, sigma B R 120 is sigma A. So, sigma A into sigma B is just R 240. So, this is also equal to this, and similarly this is equal to sigma C inverse R 120 sigma C. Okay. That means now if you look at all the if you look at all the elements that are conjugate to R 120, you only get R 120 and R 240. Okay. So, therefore, R 120 and R 240 they form a class. Okay. And the last part, similarly you can show that sigma A, sigma B, sigma C form a class. Okay. So, this is a class of order 3, this is a class of order 2, this is a class of order 1, and so and you can see that each of these is a divisor of 6. So, order of the class also divides order of the group. Okay. So, so this exercise is an explicit calculation of the subgroups and classes for a group. For a very simple group, okay, this is not the same as the groups that we will be discussing when we are talking about symmetry operations, because this is for a planar figure and we are looking only at symmetries in a plane. Okay, but the next thing we want to do is to consider the symmetry operations in various molecules. Okay, so that will be the next thing that we consider. Okay. So next we will talk about symmetry operations and symmetry elements for a molecule, for a typical molecule. Okay. Now, there are these are the symmetry operations and symmetry elements that are considered, and these are the ones that are relevant to various for describing the spectral signatures. Okay. And so it helps to classify molecules based on what symmetry elements they have. Okay. So, that is what we are going to do today. So, we are going to describe what are the various symmetry elements and symmetry operations. Okay. So, there is a distinction between symmetry operation and symmetry element. Okay. Sometimes the same symbol is used for both of them. Okay. Symmetry elements are typically these are geometric entities. These are, as they said, operations. Okay. Now, there are 4 relevant symmetry elements, and or actually there are 3 relevant symmetry elements, and corresponding to that there are 4 relevant symmetry operations. Okay. And the 4 symmetry operations and the corresponding symmetry elements are the following. So, first is reflection about a plane. This is the corresponding symmetry element is your plane. Second is inversion about a point, and that the symmetry element is a point. The third is rotation about axis. Here so you have a line or the axis, and the fourth is rotation about axis followed by reflection reflection about a perpendicular plane. So, suppose you have an axis, it is a unique plane that is perpendicular to that axis, and so we will do this, and here the symmetry element is a line. Okay. So, these are the 4 operations, okay, and that we will be considering. This is sometimes called a proper axis, and this is called a proper rotation. This is called an improper axis or an improper rotation. Okay. So, these are the symmetry elements of for any typical molecule, and these are often referred to as point groups. Okay. So, the set of all these symmetry elements for a molecule, they form a point group, and these all pass through, because they pass through one point. Okay. So, therefore, when I say rotation about an axis followed by reflection in a perpendicular plane, the axis passes through the point which might be the center of the molecule. The plane also passes through that point. So, the perpendicular plane also passes through that point. So, all these elements, they all pass through one point. Okay. This will become clear when we look at examples. Okay. So, that is what we are going to take up next. Okay. And why you can show that the set of all symmetry operations for a molecule, okay, that forms a group. Okay. So, let us look at the symmetry operations one by one, okay, and we will do this taking various examples, so that things become clear. Okay. So, the first operation we will consider is reflection about a plane. Now, consider a molecule. Let's take molecule of the form let's say Cl Br H I. So, this is a completely symmetric molecule. Only symmetry operation is the identity operation. Okay, only symmetry operation is the identity operation. Okay, and you call this molecule totally asymmetric. Okay, now suppose I had the case where I had C, Cl, Br, H, and I had a second H. Now, what are the reflections that are there in this molecule? So let us look at. So in order to see the reflections, it is easier if you draw the tetrahedral in this form. Okay, so we need to draw the molecule in a way in which we can easily see the symmetry elements. The most convenient way, this is tetrahedral geometry, where C is the center of the tetrahedron, and then you have one H, you have another H, you have Cl, and you have a Br. Br is all the way behind. Okay. Okay. Now, you can just look at this molecule and you can say that these three atoms, so the C, Cl, Br. Okay, so if I have three atoms, okay, so these three atoms, so the points corresponding to these three atoms, okay, they form a plane. So any three atoms, so long as they are not collinear, okay, they will form a plane. And so these three atoms are not, they are not on a line, but they form a plane. So if I take the plane containing these three atoms, okay, then that plane you can see, so that is this plane. This plane clearly is a plane of it has a symmetry of reflection. So if I reflect about this plane, then this H will come here, this H will go here. Okay, so this plane form a plane. This is a plane of symmetry. Okay, so in other words, if I had a mirror here, a two-sided mirror, and I reflected about this mirror, then this H will come here, this H will come here. The atoms in the plane won't change at all. Okay, so then I'll get a configuration that looks identical to this, or that looks similar to this. Okay, so it's equivalent to this. So this if I call this H1 and H2, so if I reflect about this plane, about plane, what I'll get is I'll get H2, H1, and everything else where it is. So everything else where it is. So the C, Cl, and Br will be at the same place. So the Cl will be where it is, C will be where it is, and Br will be where it is. Okay, so the point is, when I reflect about this plane, all I'll do is switch these two. Okay, and so this is an equivalent configuration. And so when you get an equivalent configuration by performing this reflection operation, then this is called a symmetry operation. Okay, so that means this is a plane of symmetry. Okay, now there is a notation that is used, a standard notation that is used for the planes. You use sigma for the plane, and there are two kinds of planes. There is one that is called sigma d and sigma h. Or sorry, sigma v, sigma h, and sigma d. Okay, these will become clear when we talk about various molecules. The definitions of these will become clear. Okay, this is sometimes called the horizontal plane. This is called the vertical plane. This is called the dihedral plane. Okay, so when we consider specific molecules, each of the meaning of all these will become clear. So we can see that CH2 ClBr has a reflection, has a symmetry element that corresponds to a plane such that you reflect about that plane and you get a symmetry operation. Now, suppose you had a molecule of this type, suppose you had an A, B, 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 okay, this kind of molecule, a planar molecule, okay, planar. Okay. Now, this has one plane of reflection. If you reflect about this plane, okay, if you reflect about the plane containing AB cube, then it's that's called a sigma H. So, now suppose you consider a molecule, a planar molecule of this shape AB cube. Okay. So, it is a planar, it is triangular in shape. Okay. Then what you can see is that it has the plane containing AB cube. Okay, this plane is a symmetry plane, it is referred to as sigma H. Okay. Then you have planes perpendicular to sigma H, and so you have planes perpendicular to sigma H, and I won't write the details, but basically there are 3 planes perpendicular to sigma H. So, one plane is this plane, the other plane is this plane, and the other plane is this plane. So, these are called sigma V prime and sigma V double prime. Okay. So, this is an example. Now, suppose you had a molecule like A B4. Suppose you had a molecule like this. Okay. Then in addition to these planes, so these planes are called sigma V. So, in this case you have sigma H, 2 sigma V's. Okay, so, you have 2 sigma V planes, which are these 2, and you have these 4 of these planes, which are or 2 of these planes. Okay, 2, and these planes are called sigma D or dihedral. So, these are called sigma D, which is passing in, which passes in between these bonds. Okay, so they are sometimes referred to. This is just nomenclature that is used typically. Okay, so sigma refers to both the plane and the symmetry operations. Now, you can see that if you reflect about this plane, you will get an equivalent configuration. Okay. And so, this is a symmetry operation. These are called sigma D prime, this is sigma V prime. This is just the conventional notation. So, this is the notation that is used in group theory. Okay. So, that is as much as I want to say about reflection. There are just a couple of more examples I want to give, so that you know how to count the reflections. Here let us so we started with CH, we had CH2 Cl Br. Okay, now if we have CH3 Cl, if you had CH3 Cl, then we have three reflection planes. Okay, and it is not hard to see, they contain the C, H and or C, Cl and one of the H's, the 3H. Okay, so just to show you, this will look like this. So, if you have so if you had this, and then here and here, if you had these 4, okay, the C is at the center. Okay, let us make this H, 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 Cl. Okay. So then you can consider various planes. So one containing CL, C and this H. Okay, so that will go like this, and it will essentially, when you reflect about it, this H will go here and this H will come here. Okay. Next you could have a plane containing this CL, the carbon and this. So that will essentially be in between these two. So when you reflect about it, this H will go here and this H will come here. Then you could have C, CL and this H, and that will essentially go in between these two. So it will be a plane that goes in between these two. Okay, and what will happen is it will switch these two on reflection. Okay, so you have 3 reflection planes for CH3Cl. If you had CH4, if instead of a Cl you had an H here, okay, if you had CH4, so for CH4 you can have 4, and you can choose any of the 2 hydrogens and the carbon atom, okay, and there are 6 ways to choose it. So there are 6 reflection planes. Okay, so that means you take a carbon and select any 2 hydrogens, okay, and the plane containing those 3 atoms will be a plane of reflection. Okay, so CH4 has 6 reflection planes. Okay, so that's how much I want to talk about reflections. When we actually do examples, it will become more clear. So next, let's talk about the next operation, which is inversion about a point. The symbol used for this is I. Okay, so there are some molecules that have this point about which you can do an inversion. Okay, so the one example is your A. So a planar molecule of this form. Okay, so this is the point of inversion. Okay, when I invert the molecule about this point, I put B here, this B here, this B here, this B here. Okay, so if I call it 1, 2, 3, 4, if I do an inversion, I will get A, B, 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 B. Okay, but then I will have 3 here, 4, I will have 2, I will have 1. Okay, and this is an equivalent configuration. Okay, so whenever a molecule has a property that if you invert about some point, you get an equivalent configuration, then that inversion, that point is a symmetry element. Okay, and inversion about that point is a symmetry operation. Okay, so there are some examples of molecules that have a point of inversion. For example, SF6. So SF6 has a point of inversion. Okay, so this is a classic molecule that is known to have a point of inversion. Similarly, if you just had a linear molecule like B, A, B, then A has a point of inversion, and so on. You can immediately see that if a molecule has to have a point of inversion, then other than the molecule on the center, all the other atoms should appear in pairs. Okay, so if I had, instead of A, B4, I could also have had A, B, B, C, C, D, D. Okay, so this molecule has a point of inversion. Okay, so this has a point of inversion because all these molecules are appearing in pairs. Okay, so that is a necessary condition. It's not sufficient because not only do they have to appear in pairs, but the pairs have to be situated opposite to each other about the central molecule. Okay, so the point is, suppose you had a molecule like AB3, C, then you know that this cannot have a point of inversion. Okay, because if you take A as the center molecule, then neither does B and C appear in pairs. If you take B as a center molecule, then clearly A and C do not appear in pairs. If you take C as a center molecule, then A and B do not appear in pairs. Okay, but on the other hand, a molecule like A, B2, C2, this could have a center of inversion if A is at the center and B's are situated opposite each other. Okay, if you have something like this, A, B2, C2, then it could have a center of inversion. Okay. So necessary condition is that other than the central molecule, the other atoms should appear in pairs. Thus, other than the center atom, the atoms should appear in pairs. Okay. The other well-known example for a point of inversion. Now, you need not have a molecule at the point of inversion. You could have a case like C H. Okay, the ethylene molecule. Now, this has a point of inversion right here. This is a point of inversion. Okay. So, you can see that all the molecules appear in pairs about this. All the other atoms appear in pairs. Okay. So when you invert about this, then this hydrogen goes here, this carbon goes here, this hydrogen goes here, this hydrogen comes here, this hydrogen comes here. So in the next class, we will talk about proper axis and improper axis. I will just mention that a proper axis is denoted by a C and an improper axis is denoted by an S. Okay. So a CN and Sn is what we will use. Okay. And this is used to signify rotation. This is used to signify that you have an axis about which rotation is a symmetry operation. Okay. So I'll just briefly mention these now, and then we'll continue to the discussion in the next lecture. So proper rotation. So Cn means rotation by 2 pi by n, by angle 2 pi by n. Okay. So for example, if you had a molecule like A, B, B, B. Okay. Now if I take the axis that passes through A, so if I take the axis that is perpendicular to the board and passes through A, okay, now I can rotate by 120 degrees, then I get an equivalent. I rotate by 120 degrees, then I get A, I get an equivalent configuration. So if this is 1, 2, 3, then I get 3, 2, 1. Okay, so this is a symmetry operation. This is denoted by C3. Okay, so C3, because C3 means rotation by 2 pi by 3 radians. Okay, so 2 pi by 3 radians is equal to 120 degrees. 2 pi by 3 is 360 by 3, that is 120 degrees. Okay. So this is a proper rotation, and we will look at examples of this soon. The other thing is the improper rotation. Okay. So this is rotation followed. So rotation by 2 pi by n radians, followed by reflection in perpendicular plane. Okay. So we'll do this in the next lecture. We'll look at examples of each of these in more detail. Okay. Now clearly, if a molecule has, if each of these is a symmetry element, if rotation by 2 pi by n is itself a symmetry element, okay, and reflection is also a symmetry element, then clearly their product will be a symmetry element. Okay. That is actually a very trivial case when you have an Sn, when you have both a Cn and a sigma perpendicular, but there are cases of molecules where you have Sns where you do not have Cn and sigma perpendicular, you still have an Sn. Okay. So this is where we will continue in the next lecture.